In this work, photoparalytic spectroscopy is used for optical absorption coefficient measurements for polymeric colloidal suspensions, Guar water solutions of different concentrations in this case. On the first place, let me give you a brief explanation about this technique. Photoparalytic spectroscopy is based in photothermal phenomena. These are physical phenomena which takes place due to heat generation after absorption of modulated radiation. There are a lot of applications of photothermal techniques. They can be used for thermal and optical characterization, for qualitative and quantitative analysis, and medical applications, among others. The qualitative description of this technique involves the heat diffusion problem across various layers, 2 layers in this case. In this model, S and W media absorbs radiation according to the Bird-Lambert model, with optical absorption coefficients beta sub S and beta sub W. The set of differential heat diffusion equations must be complemented with the usual conditions of heat flux and temperature continuity across the interfaces, and the limiting conditions of vanishing temperature as X goes to plus or minus infinitum. The analytical solution is very complicated, but in the appropriate theoretical conditions, it reduces to this very simple exponential expression. In this, H is a complex constant independent of the sample thickness. The amplitude decays exponentially with the optical absorption coefficient, as is evident. Here is a cross-section of the experimental setup. The layer between sample and paralytic sensor is a protection material for this last. This is a picture of the actual photoparalytic setup in my lab. Diode laser at 1550 nanometers was used as a light source. Here I show experimental results for the Guar Goma at 0.5 grams per 100 milliliters. 17 experimental data were taken for the analysis. The left plot shows the sample thickness range where the photoparalytic phase is constant and where a confident linear fit can be done. The corresponding optical absorption coefficient is the slope of the base linear fit, as it is shown at the plot at the right. These 2 plots show the corresponding results for the Guar Goma at 1 grams per 100 milliliters. This table summarizes the set of optical absorption coefficient values for all samples. The behavior of this optical parameter as a function of the Goma concentration is shown in this plot. It's evident here the linear behavior showing that the Bird-Lambert model applies at this range of concentrations, no matter the high scattering characteristics of these colloidal suspensions. It's worth to advise that this kind of linear correlation is not possible to be obtained for the absorbance measured by means of a conventional spectrometer. Finally, since the optical absorption coefficient is the product of the absorptivity and concentration, this important optical property, at 1550 nanometers in this case, can be obtained as the slope of the base linear fit, as it is shown on the same plot.